Everywhere we look in nature, patterns repeat themselves. The curl of a surfing wave, for example, is mirrored in clouds and on other planets like Saturn. And now they've been spotted in the Sun's atmosphere. This shape of wave is often formed by something called a Kelvin-Helmholtz, or KH instability, in which two fluids flow by each other with different speeds or densities.
For example, in clouds, yes, you have one layer where there is a cloud, okay, and then a higher layer where you have a jet stream. So at the boundary between these two regions, you start seeing this cloud rolling up. If you look at water waves, the wind will sort of cause it to roll up into a bigger and bigger wave, but eventually this wave will break. This is very similar to the Kelvin-Helmholtz instability that takes place on the Sun, where we have erupting plasma and we have stationary plasma in the Sun.
Spotting a repeating pattern like this is always good news. Since scientists already know that the movement of the waves transfers energy to the water, they know that the same thing should be happening in the Sun. That extra energy helps explain how the Sun's atmosphere, or corona, heats up to some 1,000 times hotter than the Sun's surface. These waves were spotted in the second coronal mass ejection, or CME, recorded by the Solar Dynamics Observatory, which began looking at the Sun in March 2010.
We were able to see as the CME erupted, it generated basically a region where the plasma was evacuated. Since the material from the CME lifted up into space, we see a dark region that corresponds to the low-density region evacuated by the CME. And we see just adjacent to it a brighter region where we have denser plasma. So now we see a region where the vortices start to roll up.
Astronomers have long thought that turbulence in the corona might help heat it up, but solar observations still can't see the way the atmosphere moves at small scales. Each of the rolling surfing waves spotted by SDO is about the size of the United States, and they likely became more and more turbulent the same way that a breaking water wave froths at its crest.
So it is a way of taking out the energy from the shear flow and converting it eventually into heat.
Some scientists thought that the Sun's powerful magnetic field would prevent KH waves from forming, so the heliophysicists who observed the turbulence on the Sun needed additional evidence.
To support this interpretation, we also developed a model, and a computational numerical model. We set up this model to resemble what takes place in this region, and we see that indeed this kind of shear can form Kelvin-Helmholtz instability and generate the waves that are similar to the waves we observe in nature.
A good surfer understands those waves intuitively. Thankfully, scientists understand them physically too. Watching how they roll around the Sun opens the door for more research and better solar models, helping scientists predict the activity of the star we live with.
One of the things that interests me about the Sun in particular is the fact that it is this hot, dense plasma sitting in the cold vacuum of space.
Plasma is often referred to as the fourth state of matter. So if you have a solid, you can heat the solid and turn it into a liquid. So first to second. If you heat the liquid, you can turn it into a gas, the third state. But if you keep heating your gas, you can actually rip apart the atoms that make up the gas, and you can tear the electrons from the atoms. And then you end up with a plasma, which means you have a soup of positively and negatively charged particles.
I think that plasma still invokes some sense of mystery when you hear that word, and that maybe we think it is some kind of exotic and uncommon substance. And what we want to do this evening is show you that actually it's a very interesting and a very abundant substance.
As a space scientist, I'm extremely interested in plasma because 99% of the known universe is in a plasma state. I mean, most people in their day-to-day lives don't necessarily experience a plasma. Maybe they're familiar with it because we have so many plasma TVs now, but as a space scientist, it's absolutely fundamental to understanding the universe.
We're looking at the plasma here, which has a temperature of about 80,000 Kelvin, 80,000 degrees centigrade. So incredibly hot gases. And it's actually helium which is giving off the light at this temperature. If you heat helium enough, you can make it shine in the ultraviolet light.
I study our local plasma sphere, the Sun. So the Sun's outer atmosphere is a very hot plasma, and it actually is a very interesting physical place to study, and it is also something that really does directly impact us here on the Earth as well.